Logistical things are that I assigned the first homework on Wednesday, I believe, so it should be due on Wednesday of next week. So hopefully you've started taking a look at that, or at least making sure you can access Pearson. And again, if you are looking into that and you're running into trouble, I went over it on the first lecture, which the recording is posted for. So hopefully that'll help. If that doesn't, please email me and we'll get it worked out. We still have a bit to go, so we don't have to worry about it soon, but just be aware that we will end up having a quiz for chapter 2 once we finish it. I will go ahead and get going now. Talked about Aristotle's ideas on motion and how they were all wrong, pretty much, but they had a little grain of truth to them in that the way things move can be divided into either some intrinsic property they have, he called it their nature, we're going to call it inertia, and be more specific on what that property is. And then it can be changed by a push or pull. Now, he said the only way that something's motion can be sustained rather than it eventually coming to rest is from that push or pull. That's something we're going to disagree with and say that things naturally want to keep moving, actually. Pushes or pulls are what tend to bring them to a stop. So that's the one thing that is the reverse of what Aristotle said. And it's one thing that Galileo realized as he was doing his experiments. He stated that if nothing interferes with a moving object, it'll keep moving in a straight line forever without any push or pull needed. And so we started going through one of the experiments he did to try and justify this. Obviously, a ball rolling down a hill gains speed, one rolling up a hill loses speed. But that should logically mean that right in the middle, just between those two extremes, there will be a point where something doesn't speed up or slow down. And that point should be when you're on a horizontal surface. So we know that's not the reality of things. Things do eventually come to a stop, even on a horizontal surface. But what Galileo said is even that is one of these pushes or pulls that changes motion. So it's an interference with the natural motion of the ball. If we didn't have that friction, that ball truly would keep moving forever. So friction's the thing that messes this up just a little bit. And so he said, well, if I can remove or at least reduce that friction and see that the ball rolls for longer, that should mean that eventually there will come a point where with no friction, the ball would truly roll forever. So he just used smoother and smoother things, rolled the ball on them, and saw that they did tend to roll for longer and maintain a pretty much constant speed for a greater amount of time. So his conclusion was if we did not have that friction, or of course, someone standing in front of the ball and pushing back on it or something, that object, the ball in this case, will move forever without any changes in its speed. And so this takes what Aristotle said about things naturally want to come to a stop and flips it to say, no, things naturally want to keep going. The thing that tends to bring them to a stop is stuff like friction or air resistance. Okay, so we call that property that things have that makes them want to keep moving the way they're moving inertia. It is the property of not just inanimate things, but everything, all matter, to resist changes in motion. You have this, I have this, anything you look at around you has this property, this inertia, this resistance to changes in motion. You could also think of it as just laziness. Things want to keep doing what they're doing. But it is just a property, not an explanation for why things do that. The explanation is we have no idea. Even modern day physics has no idea why things just want to keep moving the way they're moving. We really truly don't know. And that is kind of wild because that seems like such a simple thing, but that's the idea. The more basic, the more down the rabbit hole you go, the harder it gets to demonstrate some of these things. Eventually, some things you just have to say, well, that is what's happening. That's all I can say. But we can say that some things have more inertia than others, more resistance to changes in motion, and that would be the things that have more matter or made up of more stuff. So how do we measure the amount of matter in something?
The greater friction, the greater inertia.
So friction would tend to bring things to a stop sooner, right? So it wouldn't make something resist changes more. It would actually be the change that brings something to a stop. What do you think is harder to stop between, let's say, a huge 18-wheeler and a little compact car?
The 18 wheeler,
Okay, so what's different about it?
it has more mass.
More mass. There you go. So the more stuff making something up, the more material it's made of, that's what gives it more inertia. And so bigger things are harder to bring to a stop. And you may notice if you got something sitting in the back of your car and you have to suddenly brake, the big things are the dangerous ones because they really don't like to come to a stop. The small things are pretty easy. They may just hit something else and come to a stop. So inertia is this fundamental property that everything has, and we do not know why they have that property, but they do. And Aristotle didn't know that because he always thought friction was a thing no matter what. In everyday life, it is, to be fair. But we know from experiments where we have been able to pretty much remove the friction that if there are no forces acting on something, it continues to move the way that it is moving. That actually ends up being essentially Newton's first law of motion, one of his three famous laws. He pretty much just, I don't know, looked over Galileo's shoulder, copied his notes, and wrote it down, and people call it Newton's first law. So we call it the law of inertia, and it improves on it a little bit in the sense that it's a little bit more exact what it says. Newton's first law states every object continues in a state of. So we have two things that could happen. If something's not moving, so it's at rest, it'll keep doing that. The other case is uniform speed in a straight line. So if something is moving, it likes to keep moving in a straight line at the same speed. The only thing that will change either of these states is a non-zero net force. So unless acted on by a non-zero net force. You can think of that as roughly a push or pull, but we're going to be very descriptive of what a net force is in just a little bit. This is a very convoluted, dense phrasing of things. My phrasing is things want to keep moving how they're moving. If they're not moving, they want to keep doing that. If they are moving, they want to keep doing that in exactly the same way they're doing it at a certain moment. The only thing that'll change that is that non-zero net force. So we're going to break this down a little bit more and look at some examples. So the most important word in the entire law is continues. So if something's at rest, we said it likes to stay at rest. It continues in a state of rest. Probably the example that everyone's seen is this one. Now, this is, I guess, the modern version for rich people. We saw that the dishes were at rest, and even though the tablecloth was ripped out from under them, they remained nearly at rest. The nearly is because there was a force of friction acting on them from that tablecloth, but it was small. And so their tendency was to remain at rest. That was what they wanted to do. Usually, stubbing your toe is a good example of something else having too much inertia. Because if you think of you're just walking along and your foot hits something really light, then it just moves off pretty easily. It takes little force to move it. But if it hits something with a lot of mass, you walk into a dumbbell that's sitting on the floor, or you walk into a chair, it has so much inertia that it doesn't want to move. And that leads to a large force being exerted on you. We'll get to how forces work between things later, but the idea is it didn't want to move. I have another one that I want to show you. So I usually would do this in class, but I just had to record it this time. So I've just got a Jenga tower, and hopefully you can see at the bottom, I only have one of the three blocks. I've removed the outer two. I'm going to try and slap that bottom block out without knocking over the rest of the tower. If I had more blocks stacked on top of this, would it be easier or harder?
Harder.
Okay. And so if I had less blocks stacked on it, it would be easier?
Yes.
Okay. All right, well, let's see what happens with this attempt first, and then I'll tell you what I think on those other cases. Knocked the block out from the bottom. I'll do one quick replay. And the rest pretty much did not move. So if we think about what's feeling a force and what's not, that bottom block is the only thing actually feeling a force directly from me, hitting it with that meter stick. The rest of the blocks are just feeling friction from the blocks beneath them. That force is much weaker than the one I exerted on the bottom block. So it really ends up moving because that's an outside force, something to change its motion. While the others above it don't, because there's not a very significant force on them to change their motion. And so their tendency, the thing they want to do, is remain at rest. And so they do, roughly. As for that question of if I had, let's say, less blocks, it would actually become harder to do. The blocks would actually fly off in all directions at a certain point. You could even think about if I had just that bottommost block and then one layer on top of it. That's actually very hard to do, keeping the top layer of blocks at rest. Why?
Is it because the surface level of the top is kind of equal to the surface level of the bottom? So if you try to knock the bottom off, you're disturbing the top surface level and making it have more friction.
So it's not really about more friction. Actually, the top layer would be experiencing less than it did before when it had all the blocks sitting above it. Something else.
Is it because it has more inertia, so therefore it's hard to move?
There you go. And why does it have more inertia?
Because it has more mass?
Yeah, there's more blocks there. There's more stuff. So the more inertia you have, the more resistance to motion. That's what inertia is. And so it actually becomes easier to knock the bottom block out with more blocks stacked on top of it. If I stack it really high, eventually there will come a point where that's not true. That has to deal with something else called stability and where the center of gravity of that tower ends up sitting compared to the base. We'll talk a lot more about stability in a long time. So slapping out a Jenga block. The other case, if something's moving, it continues doing that without turning or changing speeds if there's nothing, no forces acting to cause those things. Okay, so the natural tendency of something, if there's no forces on it, is to keep moving in a straight line at constant speed. I think you experience that every day. If you're driving in Memphis, you'll know what I'm talking about.
Like you, since it's not changing, I assume like when someone speeds past you, you like feel like their car is like shaking. Or if you're next to someone and their music's like loud, you can like feel it.
So that is something a little bit different, but also some interesting physics there. That's something called the Bernoulli effect. We could maybe talk about that at some point. But this, I'm thinking like you, the driver, you feel this when you're driving.
When your body moves, when you're taking the car?
Yeah. So if someone comes to a sudden stop in front of you, you have to suddenly stop. What does your body do?
It like jerks back.
Does it jerk back initially?
Well, no, not initially. Like you're in
So
the
what?
front and then and then you like back up as like a kind of like an after effect.
Yeah. So what happens first?
You jolt forward.
Yeah. And if you brake really hard, you might accidentally bump into the steering wheel. And if it's a hard enough crash, that's why we have airbags to stop that from happening. So that happens, you jerk forward because of your inertia. The car stops, but you are not ready to stop yet. There's not been a large enough force on you to change your motion. So you're still moving at the speed the car was going before you braked. So braking suddenly. Your body keeps moving at the speed you were going. And that motion does not change until an outside force acts on you. Where does that force come from?
Seatbelt?
Yeah. So that's what the seatbelt is for, is to be that outside interference, that outside force that changes your motion.
So that's why they tell us to wear those seatbelts and those PSAs.
Yes, because what's the ultimate case of this? The very short stop, and if airbags don't come out, your inertia keeps you moving at 50 miles per hour, while the car is maybe at 0 now. So you fly through the front windshield. That's really the big reason, is like there's enough safety inside the car to keep you okay even in a bad wreck, but if you keep going past the car, there's not a whole lot of airbags out on the road for you. So the seatbelts, it's supposed to be that thing that can apply a large enough force to stop your motion. In the reverse case, what happens? What do you feel if you have to suddenly accelerate, speed up?
You kind of like stick to the back, like your body like leans back almost.
Yeah. And so what's really happening there is not that you're leaning back. I know it feels like it. I absolutely agree. It feels like it. What's happening is you're not ready to move yet, but the car is moving. And so your motion lags behind it. The only way you end up catching up is from that force from your seat pushing on you. So really it's the seat pushing forward on you that changes that motion, not you being pushed back into it. If you don't have a headrest, what happens?
A broken neck and possibly a broken spine.
Yeah, like a big whiplash accident. That is the same thing. It's that, okay, maybe your body's ready to move now because you got the seat pressing on your back, but you have nothing pressing on your head. So your head's not ready to move with the rest of your body. It stays behind while the rest of your body keeps moving forward. In the most extreme cases, I guess it really does stay behind, but otherwise you just end up with a bad neck injury. So inertia is a good thing and a bad thing. It can let you, coast down the road without using too much gas, but it can also kill you. So it's a property that we got to be careful with and acknowledge that we have. We'll talk about another one later. So that turning piece I've not said much about. When you take a left turn in your car, which way do you feel like you're being pulled?
The right.
To the right. Anyone got a reason for why?
Is it because like the force of you turning to your left, you're like you moving the steering wheel to your left, but your body's going to the right because of like the motion of the car?
So I guess my first point here is you're really not feeling a force to the right. As much as it feels like you are, nothing's pulling you to the right. But inertia does make it feel like that. So if we're looking at an overhead view, the car's turning left. Before it was doing that, you and the car were going straight. Your body's tendency, until there's a large enough force on it to make you move with the rest of the car, is to keep going straight. But where is that relative to the car? It's towards the right side of the car. So you want to keep moving the way you were moving, but because the car ends up going to the left, you feel like you're pulled to the right. But I'll cover that one in a lot more detail down the road. I just want you to realize that's a case of inertia too. And then last thing, just to show you a video for this, another case of inertia, which I hope none of us ever encounter, but maybe you've seen this one. How is inertia playing a role here?
Is it when it hit like slides?
Yeah, because what's he trying to do, but what's his inertia telling him to do? What's the difference between those two things?
He's trying to turn the corner, but
Uh-huh.
I get like he ran a little like too fast, so now he's sliding, which in a sense is slowing him down.
Yeah, so that inertia of his body is trying to make him keep going down that corridor and smack into the wall rather than take the turn. The only thing that's letting him take that turn is the friction between his feet and the ground, and then if he puts his hand on the wall to help him push in the direction of the turn he's trying to take. So, like you said, he's really not doing this very effectively because he's gone too fast to take the turn. That's also why cars skid out towards the outside of the turn on an icy road because of their inertia. And he's not getting enough force to go in the direction he wants to go. Now, the cheetah, it can do it a little bit better, but you notice it has plenty of inertia too. See, so it's kind of skating on the wall a little bit, but it's trying to push directly off the wall. That's going to be more effective than just the friction from the ground. All right, so inertia is this property that shows up in everything. It's why your groceries fall out of their bags when you break in your car. I dare you to go a day without having inertia show up somehow. It's why you can shake a ketchup bottle and have the ketchup fall to the bottom for you so that it'll come out instead of the gross ketchup juice stuff. So inertia is everywhere. I want to see if you're clear on the difference between these views of motion, Aristotle's and Galileo and Newton's. So basically the incorrect view and then the correct view. We got a hockey puck sliding. It comes to rest after a very long time because it's on ice. So how would each of these people have interpreted this behavior? What would Aristotle think?
When you think it was impossible because we found medium.
So there is a medium, and that would be, for one, the air around the puck, and then the ice it's sliding on. So not having a medium means like you're in empty space, complete vacuum.
Hockey puff was slowed down to want to be at rest.
So yeah, because for the puck, that is apparently its natural state of being, according to Aristotle, right, is rest. And so that's what the puck is eventually doing. It's seeking its proper place or its natural state of being, which is being at rest. And since it is of the ground, it is made of things from the ground, it wants to be at rest on the ground. Okay, what about Galileo and Newton? So this modern view of motion. So why does the puck slide for a long time, and why does it eventually come to a stop?
Since it is like in a state of moving and motion, it will eventually slow down because of one, the friction it has with the ice, and the force, the impact of force that it initially has, like lowering itself because the farther away it gets from the, what you call it, the point, the force point.
Like the hockey stick?
Yes.
Okay. So let's look at that bit actually. So the hockey stick is actually exerting a force that changes the state of motion of the puck from rest to moving. So the puck wanted to remain at rest due to its inertia, but then a force acted to change that motion, and now it is moving. Once it is moving, what does this inertia tell it to do? What does the inertia say it should do?
To move in like the straight line or the direction that it was hit at.
Yeah, so the tendency of the puck is to stay in motion, but like you said, there is another force acting to change that, and that is friction. So the puck has a tendency to maintain its motion. That is its inertia. But friction, a force, eventually brings it to rest. Never think of inertia as an actual reason for things to happen. It is just the property that things like to keep moving. So in the same way, we'll see that Newton's laws are just a observation of how nature works. There's not really any further backing to them. We don't have any further backing to inertia other than that we've just observed it in everything we've looked at. So I don't have like, well, the atoms do so and so, and therefore inertia happens. Just think of it as a property, even if I happen to word it in a way that makes it sound like an explanation for something. We've looked pretty thoroughly now at continues in a state of rest or uniform speed in a straight line. Let's look at net force now, this thing at the end. Let's be specific about what that means. So you can change the motion of something with a force, so a push or pull, or a combination of forces. Okay, so that is our working definition of a force, is a push or pull. What are some examples of forces?
Interaction with like an object, like interacting.
Yeah, so I'll put that over here. We call those contact forces. So those are actually an example of what's called an electromagnetic force. Physicists like to, this is going to be another tangent of mine. Physicists like to simplify to the least number of possible things to describe something. So we are going to mention several forces here, and I'll go ahead and say a couple. So the gravitational force, the thing that's keeping us on the ground right now, and the thing that makes stuff fall if you let it go. So this is what we experience every day as weight. There's also the electric force. So used to static electricity.
Isn't there an applied force? I've heard of that before.
I would group that into contact forces.
Oh.
It can just be from any outside thing. Usually we think of it as like a person or something mechanical, but yeah, absolutely.
Okay. I've also heard of tension forces as well.
Yeah, that's a great one too. We'll talk about that one. So tension, attract charges in your hair. So if you've ever rubbed a balloon on your hair,
I have many times.
yeah. So it makes your hair stand on end. That is an example of an electric force. There's magnetic forces. So we just think of that as magnets. There are other cases where this type of force shows up, but we won't talk too much about those. So magnets attracting or repelling. Okay, and then there's friction. There's something called a normal force, but we can actually lump these down even further. And that's what physicists have done in the last 50-ish years, is we now think that there are at most only 3 different types of forces. So those types are gravitational, electromagnetic, which is a combination of the electric and magnetic force. They're actually 2 parts of the same thing. Something called a strong nuclear force, which is what holds nuclei together. And then something called a weak nuclear force, which shows up in radioactive decay of things into less massive isotopes. And so that weak nuclear force has been united with the electromagnetic force. So the 3 that we think there are now are gravitational, electroweak is what it's called, and strong nuclear force. But we're going to talk about these that we've written instead, because it's easier to think of specific examples of those. So friction is an example actually of an electromagnetic force. If you look at the atomic level of one thing sliding over another, It's actually atomic attraction that is causing that friction. If we look at just one of these acting on something, it's not too bad to deal with, but usually more than one's acting. Right now, just sitting there, you've got gravity pulling you down. You've got what's called a normal or support force keeping you up. If you're sliding on your chair, you've got friction acting on you. So we got to think about all of those together. And that gets complicated pretty fast if we don't come up with a better way to think about them than looking at each separately. What we do is talk about what's called a net force or an effective force acting on something. You got like a tree stump or something stuck in the ground. You want to pull it out of the ground. So you pull and a friend pulls. We'll call this the force you exert and the force your friend exerts. Rather than thinking about those separately, what is the effect of you two pulling together? What is the effective force you get out?
Well, I guess like the force that you give out is like it's stronger in a sense because both of you are pulling in the same direction.
Yeah, it is a stronger effective pull coming from both of you. So rather than considering those two separate forces, we consider that effective net force. And that way we can reduce lots and lots of different forces acting to just one. You can go to 5 or 6 forces or just one. All right, so if you're both pulling just as hard as each other, that's twice in your individual forces. If your friend is an idiot and goes to the other side to pull, what is the effective force you're exerting on that stump?
It's probably the same or it's not going to do anything.
Yeah, it's like you're pretty much playing tug of war with this stump. And if you're pulling just as hard as your friend, it's not going anywhere. The net force is 0. It's as if nothing were pulling at all. Now, these are not all that exciting, I'll be honest, but just it is my job to show you that these are real things in the real world. So if you pull in the same direction, we'll start with that.
Right, I have a wooden block right here and a little dowel rod that's going to let me apply a force to it. If I pull on that, the block will move in the direction I'm pulling. If I add a second one, and each hand pulls one, that acts as if I've got me and someone else pulling. And we see that even though each hand is applying roughly the same force, we get a larger overall or net force out.
Okay, and here's me pulling on opposite ends.
If I now put the second rod over here, and I pull equally hard on both sides, we can see that even though I'm pulling pretty hard on both sides, I'll come in so you can see my hands pulling pretty hard, the net force on the block is 0, and so it's not moving.
Riveting stuff. All right, so in this second case, the net force was 0. All right, so we're going to extend on that idea of net force, being able to replace individual forces with one single effective force. So the unit we use to measure force is named after Newton. If you do enough in some area of science, sometimes you get a unit named after you in that area. So the unit of force is newtons, but we don't usually measure it in newtons. What are we used to measuring force in? Well, we said weight is an example of a force. So you step on the scale, and what do you read?
It's my pounds.
Pounds.
Yeah. So pounds are a unit of force.
I
They can
almost said
be-
kilos, but I know that's wrong.
So it's a very common misconception, and it's because we treat it like it measures weight. It actually measures mass, the amount of stuff in something. That's very closely related to weight. We're going to see the difference later. You're not wrong to think that. It's not correct, but everyone thinks that until they learn that they're different things.
Oh, okay.
Yep. Okay, so let's look at a couple examples here. So hopefully this is kind of intuitive. Let's say I pull on one side of a block with a force of 5 newtons. You can think of 1 Newton, by the way, as about the weight you feel in your hand holding an apple. So 5 Newtons is like you're trying to stack 5 apples in your hand, but it's in this case a pull that is equivalent to that downward pull you feel in your hand. Okay, so force of 5 Newtons to the right and another force of 5 Newtons to the right. What is the effective force you're getting out?
Would it just be like 1 5? So it would just be 5 altogether, or you would add them together and get 10?
So it's the second option. You add together to get 10 because, right, if you just pull with 5 Newtons of force, sure, it's 5 Newtons. But then your friend comes in and he helps you pull. He's also adding 5 Newtons of force. Overall, you should be getting out a larger force than either of you individually is applying. And that larger force is the sum of them, 10 Newtons. Okay, the second example is your friend goes to the other side of the stump and pulls. So you pull to the right with a force of 5 Newtons, he pulls to the left with a force of 5 Newtons. What is the net force?
0.
Yep. Okay, and the last one, you pull with a force of 10 Newtons. You pull twice as hard as your friend. He pulls to the left with a force of 5. What is the net force?
5.
Which way?
5 to the right.
Yeah. So how did you get that?
Subtraction.
Yeah, that's all it is. 10 Newtons minus 5 Newtons right here. This one was 5 Newtons minus 5 Newtons. This one was 5 Newtons plus 5 Newtons. So what you might notice here is that forces combine in a way that's not entirely consistent with regular numbers. Because if you put two numbers together, it's always just add them together. Here, it depends on which direction the forces are acting. That's an important thing. I'll just give you a minute to try this example. It's very similar, and I just want to see if it's making sense. So take a second on this one, and then I'll just ask what people are thinking. Okay, so we have a cart pulled to the right by a 15 Newton force and to the left by a 20 Newton force. What is the net force on that cart? I think I want to do this as sort of a poll, and I'm too lazy to set up a Zoom poll. So I'm just going to go through and ask A, B, C, or D. And when I say the letter that you think it is, just all turn your mics on and say that one. Okay? That'll also show how many people are actually here and listening right now. So who thinks that the net force on the cart is A?
Me.
Me.
Yes.
Me.
Me.
All right, what about B? Okay, no takers. C? D. All right, you all got it. It is A. If I got this block, I'm pulling with the force of 15 Newtons to the right and a larger force, 20 Newtons to the left. That is equivalent to if I were just pulling with a force of 5 Newtons to the left. And you may notice I'm trying to draw these arrows sort of to scale in the sense that the 15 Newton arrow is almost 3 times as long as the 5 Newton one. I'm not perfect at that. And the 20 Newton is about 4 times as long. If we do that, we call these arrows vectors. And it is because forces are an example of what's called a vector quantity. Has anyone ever heard this terminology, vector versus scalar? All it is, the only difference between the two things is that one cares about the direction something's pointing, so force is a vector quantity. The other does not. So scalar quantities don't care about that. So a vector quantity is a quantity whose description requires both what we call magnitude, which just means the size of that thing, how much of it, and direction. So which way the thing is pointing. Give myself a little bit more space there. Which way? Okay, so we said force is an example of a vector quantity. What else? Can you think of other examples? Okay, scalars might be a little bit easier. I'll jump to that, then we'll come back to vector quantities. Scalar quantity is a quantity described by just a magnitude, just how much of that thing you have. We don't care what direction something's pointing, if there's even a direction to speak of. Okay, so what are some examples of scalar quantities?
I assume like speed, maybe?
Yeah. When someone asks how fast you were going, like you get pulled over, for one, you just usually don't answer, or you say, I don't know. But if you knew in the back of your head, you might be thinking, well, I was going like 70 in a 50. So you're just saying numbers. You're not saying which way you were going. All right, what else?
Since speed is a factor, I also would have to assume like the distance is
Yeah.
a factor too, right?
Yeah, so distance is a scalar, just how far you went.
The velocity?
So velocity is closely related to speed. The only difference is it does care about direction. So you've actually just found us an example of a vector quantity. If you have to measure the temperature outside, does that require a direction?
No,
I
So
think in
what is,
some cases it does, to be honest.
okay, so what are you thinking as far as that goes?
When it comes to like some cases, because you know how in some areas it could be cold, but in others it could be like really hot, or even in the same area, one side could be like really hot and the other side can be super cold because that's also happened before, especially around the world.
You know what? I do agree with that. And you could talk about what's called a temperature field and talk about a gradient of temperature in that field. But say you're just holding out a thermometer. Is it capable of telling you that information if you're just holding it in one spot?
Oh, then no.
Okay, so that's what I'm getting at. In that case, what is temperature considered, a vector or a scalar quantity?
scale.
Yeah. So temperature.
I also realize since the first day we were talking about planes,
Mhm.
would like the like thrust would also be like a vector
You're
quantity?
right. And it actually is an example of a force. So what
Oh,
thrust is the jet engine. It actually pushes on the air behind it, as well as expelling some gases. Both things end up pushing the jet forward. So
Would volume be one?
volume, yeah. So that's a scalar because if we're talking about how much volume you have enclosed in a room or something, how many cubic feet a room is, you talk about that for like air conditioners and stuff. You just give a number. That's all you need. You don't need to say 50 cubic meters or cubic feet west. It doesn't even make sense to say that. So that's the distinction between vector and scalar quantities is direction. I'll give you one more vector quantity and we'll call it a day. Acceleration. Okay, we'll talk about acceleration more later too. So are there any questions before we sign off for the day?
Isn't an example of acceleration is like what I was just thinking, like the wind, like when you try to do wind directions or stuff like that?
Um, so acceleration is something's velocity changing, and that could happen with wind, where the direction the wind is blowing changes, or the wind speeds up or slows down. So acceleration is involved there. As far as like if you had a windsock that you stuck out, what it's measuring is a vector quantity too. It's wind velocity. So yeah. All right, any other questions? Okay, then I will see you all on Monday in person. Finally, thank God.